So, after having dealt with the inner product kernels, now let us begin our discussions how to optimally design SVMs, right, using this notion of inner product kernels. The expansion of the inner product kernel K with arguments x and xi allows us to construct a decision surface which is nonlinear in the input space, but with image in the feature space that is linear. This is a very important take home message, right. So, in the feature space it is linear and it is nonlinear in the input space. So, our goal would be to set up the optimization problem using this kernel function. Let us see how we can proceed. Let us construct the optimization problem, or we set up the optimization problem as follows. We would like to maximize this function q of alpha, where alpha is this vector comprising of the Lagrange multipliers alpha 1, alpha 2, so on till alpha subscript n. We want to maximize q of alpha with respect to alpha subject to certain conditions. So, following this linear separability idea, our dual problem is basically summation I equals 1 to n alpha I, this is a summation over the Lagrange multipliers, minus a term that has the Lagrange multipliers, the desired response and the kernel acting on the data points, right. So, this is exactly the same. So, in the case of the design of SVMs for linearly separable patterns, if in the input space the patterns are linearly separable, I could write it in terms of xi transpose xj like I did earlier, but just observe that there is a kernel here that is acting on xi and xj, because we are now in the nonlinear space and therefore, we have nonlinearly transformed the inputs in the feature space, and now we are looking for a linear classifier in this feature space towards this pattern separability problem, right. So, I just would mention here, observe the K as against xi transposed xj in linearly separable situation in the input space. Now, what are the conditions for this optimization problem? What are the constraints? Summation I equals 1 to n alpha I di equals 0, and alpha I is bounded between 0 and c, where c is some fixed constant, and this has to hold for all the constraints I equals 1 to capital N, right, and we have the bias details taken care of when we have to solve for the kernel in terms of the nonlinear mapping. Okay. This is an important formulation, but it is pretty straightforward. I mean, the idea is just obtained by lifting the vector in the input space to the feature space, and there you work with a linear classifier. Okay. That is the simple idea. Now, the inner product kernel, which is k of xi comma xj, can be computed for all pairs I and j from 1 to n, and you can straightforwardly verify that this is a symmetric matrix. The kernel is symmetric and this matrix is also symmetric, right. You can visualize this as a stack of kx1 x1 dot 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 kx1 xn kxn x1 kxn xn. So, this is sort of the Graham matrix that I can form from my vectors xi. Now, having found the optimum values for the Lagrange multipliers, right, I take the derivatives with respect to the parameters in the Lagrangian and I solve for the optimum Lagrange multipliers. Then I can compute the optimum weight vector W according to this equation that I have written down, which is summation I equals 1 to capital N, the optimum Lagrange multiplier multiplied by the desired response times the image induced in the feature space, the image of the input vector in the feature space. So, this is how I can compute this optimum weight vector, right. So, this is straightforward. So, now once we compute the optimum weight vector, then we can solve the pattern separability problem, and this completes the design of SVM for non-separable patterns in the input space. So, the idea is to lift the vector non-linearly in the feature space and then set up the optimization problem appropriately and then solve this optimization problem to get the appropriate Lagrange multipliers that are optimum, and then from this you can figure out your hyperplane. Okay. This completes this design. But in general, when we have non-linearly patterns that are misclassified, for example, we have non-linear separability, but we still want to put some conditions, then we follow the same math and we set up the conditions to minimize the average error for misclassification, and from that risk computation we can formulate our cost functional and proceed very similar to what we have done earlier. Okay. So, this completes our discussion on SVM design for nonlinear separable patterns in the input space.